Okay, hello everyone and welcome to today's session on the design of a capacitance sensor for void fraction measurements in two-phase flow using the software QuickField. My name is Tobias Gschnaidtner and I'm currently enrolled as a master student at the Technical University of Munich. Basically my current studies focus on energy systems and thermal processes, which includes, for example, heat transfer or fluid dynamics or any other kind or all kind of energy systems. So in this context, I have the honor to present you some parts of my final thesis. So what is the motivation using QuickField throughout my thesis? On this slide, you can see a so-called two-phase closed-loop thermosiphon, which can, for example, be used to effectively cool electronic devices. It basically consists of 4 components, as you can see here. That's the downcomer, where the working fluid is pure liquid, then the evaporator, where the heat is dissipated from the heat source, for example, the electronic devices, and the cooling fluid is basically evaporated. Then there's the riser, in which the evaporated cooling fluid is lifted by the difference in the density between the liquid phase in the downcomer and the two-phase mixture in the riser. And finally, at the top of this device, there's a condenser where the two-phase mixture cools down and finally condenses. So in order to analyze and optimize such a system, a deeper understanding of the two-phase mixture in the riser and especially of the void fraction is essential. And to briefly explain what the void fraction or term void fraction in a tube means, it's basically defined here in the right box as alpha, and alpha is defined as the ratio of the volume occupied by the gas phase and the total volume of the tube. And to be able to measure the void fraction, one part of my thesis was about the design and development of a simple void fraction sensor based on the capacitance method. And that's also the part where I used the software QuickField. So, but before I start with the main part of my presentation, I would like to give you a short overview. So first, I will describe the problem, then the applied model, as well as the method used to solve the problem. Then in the next step, I will present the numerical results based on QuickField. And before I will compare the experimental as well as the numerical results, I will briefly outline the experimental setup, including the sensor which I designed throughout my thesis. And last but not least, I will finish my presentation with a short conclusion. So here on slide 4, you can see a model of the type of the capacitance sensor here on the left, which was chosen based on a literature research, and it's called the ring type capacitance sensor according to his design. So you got basically 2 rings. And this type of capacitance sensor may be analyzed based on an analytical approach, as is also basically expressed here on the left side, by a ideal plate capacitor. However, as you can imagine, this is a very simple approach to do it with an ideal plate capacitor, and it does not take into account the non-uniform distribution of the electric field lines. So as a result, in order to optimize the ring configuration in terms of sensitivity, a numerical approach is essential, or let's say it's better. And moreover, it can be assumed that the signal of the sensor depends also on the flow pattern, and therefore it also needs to be calibrated, which can also be done numerically. And therefore, QuickField is used on one hand to optimize the geometry of the sensor, and on the other hand to show that the sensor can be calibrated based on numerical calculations using, for example, QuickField. So in order to approach the ring type sensor numerically and simplify the problem description, throughout my thesis I made the following assumption. On one hand, the effect of fringing field is neglected. Then the relative permittivity of each phase, that means of the gas phase and of the liquid phase, they both are assumed to be constant throughout the calculations. Then it's assumed that there is no free charge in the domain, and it can be seen as an electrostatic and axisymmetric problem. So based on these assumptions, the problem can be described using the axisymmetric Laplace equation as outlined here in the box. Then the numerical model for the optimization of the ring type sensor is shown on this slide. So on the left side, the problem is outlined schematically, where the both rings are highlighted in red and blue. And on the right side, you can see an exemplary numerical model as it was implemented in QuickField. Here, the boundary conditions are chosen as follows. So both ring electrodes, which I told you that they are highlighted in red and blue, they are set to a specific potential. So here it's V0 and 0. And all other boundaries are set in such a way that the derivatives of the potentials are 0. So now, to optimize the design of the sensor with respect to the sensitivity, the weights W, or designed here as W, of the rings and the gap between the rings, here it's S, they are varied. So thereby, the sensitivity is defined as the difference in the capacitance when the sensor is purely filled with the liquid phase, or on the other hand, it's purely filled with the gas phase. However, in each case, the capacitance is calculated based on the stored energy, as you can see in the last box on the left side. As I mentioned before, QuickField was not only used to optimize the design of the sensor, but also to prove the applicability of the models in order to get also a calibration curve for the capacitance sensor. So in my case, I studied the vertical two-phase flow, and commonly there are 4 typical arrangements, as you can see here on this slide. And basically these arrangements are called flow patterns. And these flow patterns are exemplarily shown here from A to D, and they encompass, on one hand, bubbly flow, which can be described as small gas bubbles in a continuous liquid phase, then intermittent flow, that means B and C, which is best described by bullet-shaped gas bubbles in the case of B, and slug flow, and rather chaotic gas plugs in the case of churn flow. And last but not least, there is annular flow, which can be described as a thin liquid film at the periphery of the tube and a gas core in the center. And in order to approach the different flow patterns numerically, here bubbly flow is approximated by the Maxwell model, and the annular flow by what I personally would call the gas core model. And these 2 models are briefly outlined on the next 2 slides. And there are still two flow patterns missing, namely the slug and the churn flow. But since slug and churn flow are of a more complex nature, here they are approached by an approximation based on the bubbly and annular flow model, which I will show you later on. And on this slide, you can see again a schematic drawing of the ring type sensor, and here it's basically for the gas core model. Here the 2 phases are separated into 2 blocks. That means the inner one representing the gas core with the relative permittivity for the gas phase, and the outer one representing the liquid film with the relative permittivity for the liquid phase. And the inner boundary condition, here all the outer boundary conditions are similar to the optimization case, and here the inner boundary condition between the 2 blocks is defined in such a way that the derivatives of the potential are equal, as you can see in the box at the bottom of this slide. On the next slide, you can see the approach of the bubbly flow pattern. And in order to model the Bubbly flow in the study, a so-called core peak radial void profile is assumed. And this void profile is defined here in the left box at the bottom. And knowing the distribution of the void fraction along the radius, a mixture, a so-called mixture relative permittivity, can be calculated. And therefore, the model given by Maxwell is used, and the model is outlined here in the right box. And in order to apply these models to the numerical model, the geometrical model, as you can see on this slide, is divided into several blocks of equal size. Here, a number of 12 blocks was chosen. And in each block, the mixture relative permittivity was set constant according to the two models. That means by the radial void profile and the Maxwell model. So, next I will just briefly discuss the chosen method, which I used throughout my numerical simulations. So in my thesis, I basically used QuickField along with MATLAB, since in this way I obtained the desired results in a more efficient way. And therefore, the basic configurations, such as the problem type, the model class, and the structure of the geometric model, were designed and solved using QuickField. MATLAB, in contrary, was used to evaluate the data and to serve as a COM client that basically defines and varies the parameters such as the physical and the geometric properties. Before discussing the numerical results, I briefly want to demonstrate the use of QuickField along with MATLAB. So in order to run the QuickField simulation using MATLAB, the QuickField model file needs to be opened, as you can see here. And in addition, it is also advisable that the QuickField file is in the same working directory as the MATLAB code. So here the present example shows the simulation file regarding the design of the sensor. And this simulation file is, this example is pretty much the same as the other two examples. Here the QuickField file is shown on the left, and here on this screen, as you can see, and the MATLAB code on the right. So to focus on the MATLAB code, the MATLAB code is basically divided into 4 parts. Here in the first part, which is labeled parameters, the parameters of the simulation can be defined, and these parameters may include quantities such as the length of the electrodes, the distance between the electrodes, the relative permittivity of the faces, of both faces, and, for example, the mesh spacing. Then in the following section, here where you can set the geometry of the model, there the initial parameters of the geometric model as well as the mesh spacing are set. Then in the next step here, as labeled calculate sensitivity, serial analysis of the problems basically carried out by simulating the specific alterations of the model geometry for the given physical properties. And then once all the results of the alterations are calculated, in the last step here labeled as plot result sensitivity over distance, the results basically are plotted in a graph. Then in order to show you that the serial analysis using MATLAB actually works, I will just run the MATLAB code, and you will see that it basically will work. So having started the compilation of the MATLAB code, you can now see that the analysis simulating the specified alterations is in progress here on the left.
Yeah, and as mentioned before, at the end, as you can see here, a graph presenting the results of the simulation is plotted.
Yeah, and the numerical calculations for the optimization case of the capacitance sensor were carried out for a relative permittivity of the liquid phase of about 1.84 and the gas phase of 1. This represents basically the case of dielectric fluids with a small difference in the relative permittivities between the gas and the liquid phase. And therefore, it's like really important that the sensor is quite sensitive, since the difference between the two relative permittivities of the gas and the liquid phase is quite small. And here on this slide, you can see the results in terms of the sensitivity depending on the widths of the electrodes and the gap between the electrodes. And the results shown here in the graph on the right side of the slide. And as you can see, by increasing the widths W of the rings and decreasing the gap between them, the sensitivity of the sensor is increased. And moreover, it can be found that the effect on the sensitivity is quite small for a width of more than 10 millimeters. So based on these findings, here the optimum design parameters in terms of sensitivity are defined as dimensional numbers and are given here in the box below. So in my study, I only conducted experiment for air distilled water to phase flow. That means, relative permittivities of 1 for the gas phase and 80 for the liquid phase. So in contrast to the relative permittivities I assumed for the optimization case, here you can see it's like 1 to 80, and before it was like just 1 to approximately 2. And since I only used air distilled water to phase flow, the calibration curves for the capacitance sensor are also only calculated numerically for this case. The results are shown here for annular and bubbly flow, whereby the void fraction, as defined on one of the first slides, is plotted over the dimensional capacitance as defined in the box on the left. And in terms of bubbly flow, 4 different cases of the model were applied, as you can see here in the right graph. However, according to previous studies, annular flow occurs most likely for a void fraction of more than 0.85, and bubbly flow in general of less than 0.2. So therefore, the resulting calibration curves are here illustrated in the graph in the middle, where the different flow patterns are restricted by the 2 red dashed lines. That means at the top there's like annular flow, so for a void fraction value of more than 0.85. Then in the middle section there's intermittent flow, that means slug and churn flow, and at the bottom from 0 to 0.2 there are the 4 cases of bubbly flow. And in order to compare the numerical calibration curves to experimental results, a sensor based on the proposed design parameters as given on one of the previous slides, and a so-called two-phase test rig was designed. And both of them are illustrated here on the next slide. Here on one hand you can see a CAD drawing of the test rig, and also of the ring type capacitance sensor. And besides the capacitance sensor, the test rig also encompasses 2 quick closing valves. And here in my study, the quick closing valves, which basically isolate one part of the test section, and then you are able to measure the void fraction, they are here used as a calibration standard for the capacitance sensor. And in order to measure the capacitance between the 2 rings, a capacitance meter here, a Bonden 72BD capacitance meter, is connected via two BNC cables with the designed sensor. And as a result, using this setup, dynamic experiments based on air distilled water two-phase flow can be carried out. And thereby, as I mentioned before, the measured capacitance can be compared to the measured void fraction based on the quick closing valve method. Here on the next slide, you can see the comparison of the experimental and the numerical results. In both of the graphs, V star represents the dimensional sensor output of the capacitance meter, which is also defined in the right box. Here the left graph compares the Annular and Bubbly flow models with their experimental data. In contrast, the right graph outlines basically the best models. That means the best Bubbly flow model for n equals 1, and a weighted average of the Bubbly and the Annular flow model in order to describe the intermittent flow. So, as I mentioned before, there's no particular numerical model that can be used for slug or churn flow, and therefore it was approximated by a weighted average. And using the proposed models, one can see that the numerical results follow the trend of the experimental results quite well, and they have a root mean square error of about 0.03 and a maximum deviation of 0.08. So to sum up, in this study, I used QuickField for optimizing and calibrating a capacitance void fraction sensor. And in this context, QuickField was used along with MATLAB, which basically enabled a simple and a very, very fast serial analysis. Moreover, as it was shown in the previous slides, the numerical results agree well with the experimental data. So in the case of air distilled water, two-phase flow, a numerical calibration curve may be applied to the capacitance sensor. So you basically don't have to do it practically, but you can use numerical tools to do the calibration of the sensor for you. But nevertheless, yet the experiments were only carried out for air distilled water. And therefore, the applicability of the models needs also to be proven for other dielectric fluids with a different relative permittivity, such as was the case for the optimization case, where one fluid, the gas phase, had only a relative permittivity of 1 and the liquid phase of about 2. Yeah, and this also concludes my presentation. So I want to thank you very much for your attention. And in case you're interested in my work, or if you want to know more detail on the numerical approach or the calculation or what else I've done throughout my thesis, I would like to refer you to my thesis, which I will publish soon. So, and yeah, in case you have further questions, just please feel free to send me an email. So again,